All right, hello. Let's take a look at example problem 5. So we are told, let me scroll down a little, we have a sealed rigid tank. All right, so keyword, sealed rigid tank. What that tells me is that my total volume, or my volume, as long as we don't remove mass, is constant. Okay, and that also tells me then, right, if I'm thinking in terms of my first law of balance, delta U is Q plus W, that if I'm only dealing with PV boundary work, that work term is going to be 0. Right? So I'm already thinking, oh great, right, it's just going to be delta U is Q. So you have a sealed rigid tank that's filled with 1 kilogram of steam at 200 degrees C and 10 bar. Great. Temperature and pressure is specified. If I have a single component, single phase system, system is fixed. A, what is the volume of the tank? All right, we've got this. So if my system is at a temperature, and I'm going to write this as, well, I don't need to write as T1 yet. So let's say our temperature is 200 degrees C, and my pressure was 10 bar. Okay. And we know from the problem statement that the mass is 1 kilogram. All right, so what I want to find out is, again, I know the state of my system is going to be fixed since we're given two intensive properties. I want to find the specific volume of my system, because then once I have the specific volume, say meters cubed per kilogram, I just multiply by the mass and I have the total volume. So let's see, I have steam tables open, and in another window I have MATLAB. Okay, so I'm going to flip around to saturated or superheated steam tables. And the first thing I'm going to do is I'm going to confirm my phase. So I'm going to go down to 10 bar. And at 10 bar, my saturation temperature is 179.89. Okay, my temperature is 200 degrees C, so my temperature is greater than the corresponding saturation temperature. So I know I have a superheated vapor. And this problem's nice, right? So if I move over to the superheated region, right, I have a column for 200 degrees C. So my specific volume is 0.2060. Okay, so from the steam tables, we find that V is 0.2060, and that's meters cubed per kilogram. All right, and so this is from my superheated steam tables. Okay, so I know V. Okay, so V total is what we're asked for. And so V total is just going to be equal to M times V. Okay, and this is a nice problem. M is just 1 kilogram. So my volume is 0.2060 meters cubed. Perfect. All right. Just make sure I've got 2060. Yeah. All right. Cool. So B. Oh, yeah. So B. Let me scroll. So now we're told 0.5 kilograms of steam are removed from the tank. If the temperature remains at 200 degrees C, what is the new pressure in the tank? All right. We've got this. So in B, okay, what's going to be key? So B, we're told our temperature is still 200 degrees C. Okay, but now my mass is just going to be 0.5 kilograms. All right, why? Because we initially had 1 kilogram. Now we're told we're removing half a kilogram. So that means I have half a kilogram left. And then the other key is, since we have a rigid tank, my total volume from part A, right, is the same, right? My total volume is constant, and so it's going to still be 0.2060 meters cubed. So with V total and M, okay, I can calculate my specific volume. So V is going to be V total over M. Okay, and interestingly, since this is half of the initial volume, right? The new specific volume is going to be double this original value. All right, so it'll be, I'll just write as 2 times 0.2060 meters cubed per kilogram. All right, so the new specific volume is double the original value. And what's key now is now I know temperature and I know specific volume. So if I had a single component, single phase system, here's 2 intensive properties. The state of my system is fixed. Okay, and so then what we can do is we can go to our steam tables and figure out where we are in the steam tables. All right, so I can answer DC at exactly the same time, what phase I have, and then we can figure out the pressure. Okay, so let's do it. Okay, so I've got a script open, so just to make note for part B. Okay, so we had V total is my same 0.2060, that's meters cubed. My mass is 0.5, and that's in kilograms. So my volume is going to be V total divided by mass. Okay, let me make this a lowercase 2. Okay. Because I called this V total. Bam. So 0.4120. And that's meters cubed per kilogram. All right, so now what I need to do is I'm going to go back to my steam tables here. Okay, and I first need to determine what phase I have. Okay, or I'm going to first determine what phase I have, which is actually the next problem. So what I'm going to do is I'm going to go to my saturated steam tables. Okay, because 200 degrees is on here. And here I find a specific volume of my liquid and the specific volume of my vapor, all right, at equilibrium at 200 degrees C. So my vapor phase specific volume is 0.1272. Okay. The specific volume of my vapor phase is greater than that of my vapor, right? So I'm going to be in the superheated vapor region. Right, and it's what I would expect, right? So I'm assuming, all right. So just based on this, right? The fact that even at 200 degrees C at saturation, my volume is greater than this. I'm assuming I'm in the vapor phase, right? But we're gonna find out. Okay, how do we find out? All right, so I go back to my superheated steam tables. And so I know I'm at a temperature of 200 degrees C. What I want to find out is my pressure. So I'm looking in this column at 200 degrees C for when I get values that bracket my answer. Okay, so it would look like I'm between 5 and 5.5 bars. Okay, so at 5 bars and 200 degrees C, my specific volume is 0.4250, and at 5.5 bars, we're at 0.3853. Okay, so let's make a table because we'll interpolate. All right, so again, we're at a temperature of 200 degrees C, and what we're trying to figure out is what our pressure is. So when I looked at saturation tables at 200 degrees C, we had a molar volume of the liquid and vapor. Our molar volume was greater than the molar volume of the vapor. So what that tells me is I'm not at two-phase equilibrium. Why? If I was at two-phase equilibrium, at that pressure, my specific volume would be between those two volumes. The fact that my specific volume is greater tells me I'm not at coexistence. So I'm assuming I'm in superheated vapor. And so what I'm doing then is, again, I'm looking in my superheated steam tables down this column at 200 degrees C, since I know I'm at 200 degrees C, and I'm trying to find the pressure where I get this volume. So based on this, right, I see that it looks like I'm between So let me make a little table. And let me make volume so we can clearly see this. So volume, and volume again is in meters cubed per kilogram. So 5 bars, and I'm going to write 5.5. At 5 bars, we have 0.4250. At 5.5 bars, I have 0.3853. Okay, so I'm somewhere in between it because my value is 0.4120. Okay, so let's figure out what our volume is. So I'm going to interpolate, or let's find out what my pressure is. Okay, and so to do that, I'm going to create a vector of my volumes. So my volumes are 0.4250 and 0.3853. I have my vector of my pressures, which are in bar. I'm not worried about converting here, and that's 5 and 5.5. Okay, so to get my pressure, okay, which would be in bars, I'm going to use interp1, so linear interpolation. First comes my independent variable, which in this case is P or V, followed by pressure, and then the volume at which I want to compute P. So running, we get a pressure of 5.1637. Pressure is 5.1637, and that's bar. Okay, cool. All right, so I have B. All right, I have that it's I have its pressure. Then C, what is the state? Okay, again, the state is going to be superheated. Okay, and the justification for that again is if I come to my saturated steam tables at 200 degrees C, okay, specific volume of my liquid is this, specific volume of my vapor is that. So if I was at two-phase equilibrium, right, what I would have to have is a specific volume between these two. All right, if I had a specific volume between those two, all right, then I could be at two-phase coexistence. Okay, but I'm not. My specific volume is greater than the vapor, so I'm suspecting I'm over in that, it should be over in that superheated vapor region. And so then what we did is we put ourselves in superheated vapor. We know our temperature is 200 degrees C. So then we look down this column to see at what pressure in the superheated vapor phase we could have that specific volume. Okay, cool. All right, and so that was our confirmation then that we were superheated vapor, since we found two pressures that bracket our specific volume, and we're able to interpolate. Okay, but key was looking at saturated steam tables at 200 degrees C. Our volume was greater than the saturated liquid, right, at that temperature, so we were not at two-phase coexistence. Okay, let me get another page. So that's C. D. How much heat must be added to bring the pressure back up to 10 bar? Okay, so let's try and work through this and take note of what we have. Okay, so my initial state. Okay, so if I think of my initial state, okay, we had just computed. Okay, and I'm going to use 1 to be my initial state. We have that, my specific volume says 0.4120. That's meters cubed per kilogram. We have a temperature of 200 degrees C. All right, and we just computed our pressure to be 5.1637. All right, now my final state. So in my final state, we have a rigid tank. So you know that the specific volume is going to remain unchanged since we're not told that we're removing any mass in this case. And are we told anything else? How much heat must be added to bring the pressure back up to 10 bars? And then we're asked what's the temperature in that state D as well. Okay, so we know the specific volume is the same, and we know that the pressure is equal to 10 bar. So again, in our final state, we have two intensive properties, so we know the state of my system is fixed. Okay, so we have enough information to solve the problem. And then, as he mentioned when we first were talking through the problem statement, right, key is if I write down my first law energy balance, delta U is equal to Q plus W. Okay, the key is that this work term, if we're assuming that we only have PV boundary work, since volume's constant, right, this term is 0. Okay, so our first law balance reduces to delta U is equal to Q. So if I want to find Q, what I need to find is the internal energy in my initial state and then the internal energy in my final state. All right, let's do it. So what I'm going to do first is to get internal energy in my initial state. Okay, I'm just going to expand this. Okay, and I can write it off to the left here. Let's get U, right? Let's set up our interpolation at the same time here, right? Since I already have the data set up to do so. So U, which is in kilojoules per kilogram. Okay. So we are 200 degrees C and 5 bar. So U is there. 2643.4. 2643.4. Then at 5.5, hold on. Oh, I'm at 2643.4, 2641.4. Okay, so I'm going to come back up here, and what I'm going to do is I'm going to add or create an additional vector for U. 2643.4, 2641.4. Okay, and so then let's also I'll call this U1. It's going to be essentially the same, but now instead of P, I'm going to have U. Okay, so U1 is going to be 2.6427 2.6427 times 10 to the 3 kilojoules per kilogram. Okay, now we need to get U2. So how am I going to get U2? Well, I'm going to go back to my superheated steam tables. So let's take this one piece at a time, and scroll up again. Get my volume. So my volume's that 0.4120. Oh, I have it right there. So if I go to my superheated steam tables, okay, first things first. At 10 bar, here's the saturated vapor or specific volume of my saturated liquid and saturated vapor at equilibrium. Our specific volume is greater than that of the vapor, all right? So I'm going to be over in the superheated vapor region. So what I'm doing now is I'm reading across in temperatures until I find our value. And so what it looks like is our value is going to be between these 2 points, 600 and 650 degrees C. So we can interpolate. We can interpolate and solve for the temperature. At the same time, let's solve for U, and then we can solve the next two problems at the same time. Okay, but key is at 10 bar, here's specific volume of my saturated liquid and vapor. my specific volume is greater than that of the vapor, so I must be superheated. And so here I am reading across the row. Okay. So let's create a table, and we will interpolate and get T and U at the same time to solve both parts of the problem. Okay. So I'm going to create a column for T in degree C. Now let's just put U here and kilojoules per kilogram. And then finally V, which is meters cubed per kilogram. All right, so we are between 600 and 650 degrees C. So I'm just going to write 600. Okay, make it clear how we're interpolating. So at 600, U is 3297.4. In the vapor phase, or at 650, 3297, 3386.1. 3386.1. Let's get the volumes at 600, 0.4011. And 650, 4245. Got it. And our volume is, again, 0.4120. So I would interpolate to find T and U. So I'm going to come back up to MATLAB. Let me call this part C. And let's start. I'm going to create a vector for T. So 600 and 650. Sorry, I keep going the wrong page. Vector for U. U is 3297.4 and 3386.1. And then V. Okay, so it's just in the way I've set up my table, the top value and the bottom value, the values right off from my table. Okay, so to get U2, I'm going to interpolate. So my independent variable in this case is V, U, and I estimate the value at, so V is the same as before, so let's put V in there. And then T2, same thing, but now I'm interpolating with respect to T using my V. Okay. So let's see. Oh, need comma. Bam. So I get U. So I get U2. Okay, and I'm basically solving the next two problems at the same time. U2 is 3.3387. That's times 10 to the 3 kilojoules per kilogram. And T2, okay, my final temperature is 623.2906 degrees C. All right, so that's a pretty big temperature increase. Okay, so this is T for the next problem. And then to get Q, okay, so Q would be U2 minus U1. So let's do it. So let's just do it up here since I have it. So Q is going to be U2 minus U1. Okay, then note, right, this is going to be kilojoules per kilogram. So that'd be my intensive specific value. And if I want the total Q, it's equal to mass, which I believe here we still have is 0.5, mass times Q. Okay, so Q is 695. $695.9724. That's kilojoules per kilogram. And if I blasted stylus, and if I want the total Q, right, that would be M times my intensive Q, and that gives me 347.9862 kilojoules. Okay. Cool. So I calculated the heat required. We've got that. And then we have the temperature E. Problem solved. Hope that helps. Let me know if you have any questions.